Welcome back to the Deep Dives. Today, we are strapping in for a deep exploration of galactic scale. We're tackling one of the most frustrating obstacles in the search for extraterrestrial intelligence. I mean, it's that immense, just mind-bending void that separates us from everyone else. And we're not just talking about distance. We're talking about the crushing weight of time.
It's the ultimate logistical hurdle, isn't it? I mean, we spend so much time discussing what ETI might look like, what tech they might have. But we often just, we ignore the brutal geometry of the cosmos. If civilizations are really far apart, the standard way of doing things, just passively listening for radio waves, the whole SETI approach, it just fails. It becomes, statistically impossible.
And that failure is really the foundation for our mission today. We're unpacking this incredibly potent synthesis of ideas, articulated by the Soviet astrophysicist Iosif Shklovsky in his big work, Universe, Life, Mind. And he's leaning really heavily on the thinking of Ronald Bracewell back in the 1960s. Their argument is it's startlingly clear. If we want to bridge that gap, we have to abandon the hope of light-speed communication. We have to embrace physical messengers.
Yeah, that's the core idea. When the time it takes to have a conversation is measured in millennia, you have to replace the radio dish with a rocket engine. So we're going to dissect why electromagnetic waves just hit this fundamental wall. It's driven by this geometric explosion of the search space, and also by the temporal fragility of technological societies. And then we'll look really closely at Bracewell's elegant solution, the automatic interstellar probe, or as Shklovsky called it, the cybernetic guest.
Okay, let's unpack this, and let's start with that first most fundamental challenge, distance, because it's not just a matter of miles, right? It's a killer of any viable search strategy. When we approach ETI communication, we usually think about the inverse square law. The further away you are, the more power you need. But the source material, drawing from Bracewell, it clarifies that distance does something far more damaging. It radically changes the fundamental geometry of the search.
That's the critical distinction. Shklovsky separates the problem into these two distinct cases. And the difficulty level, it doesn't just double or triple between them. It jumps by orders of magnitude. It's all because of spherical volume.
And case I is the incredibly optimistic scenario, right? The one that informed all those very first SETI experiments decades ago.
Precisely. Yeah, Kasai says that the nearest civilizations are relatively close, say, around 10 light years away. This was the hope behind those early projects, the ones championed by Cocconi and Morrison or Towns and Schwartz. If that were true, the search would be finite, it would be focused, and, manageable.
And how manageable are we talking? I mean, based on the suitable sun-like stars in our neighborhood, what's that search pool actually look like?
Within 10 light years, the source material identifies only 3 primary candidates: Epsilon Eridani, Tau Ceti, and Epsilon Indi. Now, if the answer to the Fermi paradox was just waiting in one of those 3 systems, well, we could deploy highly sensitive equipment and just monitor them continuously with relative ease. That's a highly targeted, resource-efficient endeavor.
But the analysis strongly implies that case 2 is the real world, that the cosmos is not teeming with tech life right next door. So what happens when that distance to the nearest neighbor goes past, say, 100 light years?
And this is where the geometric impossibility just kicks in. You have to think of it in 3 dimensions. When you move that search radius from 10 light years to 100, you haven't just increased the distance by a factor of 10. Because the volume of a sphere is proportional to the cube of its radius, the volume of space you need to check increases by a factor of 1,000. 10 cubed.
1,000 times more space.
Yeah. And if we assume a somewhat uniform distribution of candidate stars, that means we jump from 3 stars to potentially 3,000, or even tens of thousands of suitable candidates that have to be monitored continuously. The task instantly shifts from a focused research project to a continuous, large-scale industrial-level operation.
So we've gone from 3 manageable targets to maybe 50,000 indistinguishable targets, each hundreds of light years away. And that, like you said, doesn't just increase the power requirement. It completely changes the nature of the task.
It demands what the source material colorfully calls a sky service of grandiose dimensions. And remember, this operation has to cover tens of thousands of directions and maintain this monumental effort continuously for centuries or even millennia, just waiting for a signal that might have been transmitted thousands of years ago.
Let's just dwell on that timescale difficulty for a second. If our nearest neighbor is 1,000 light years away, and we'll see that's very possible, we send a message now. We wait 1,000 years for it to get there. And then we wait another 1,000 years for a potential answer.
Yeah.
The total round-trip time is 2,000 years.
That is functionally impossible for a two-way conversation. I mean, imagine you get an email that was sent 1,000 years ago, and you know that your reply won't be read until 1,000 years after you send it. The whole concept of dialogue becomes meaningless. You're left with this monumental task of maintaining technological and societal stability for 2 millennia just to exchange a single data point.
And the effort required on our end, the infrastructure you'd need to continuously focus these high-precision electromagnetic beams on tens of thousands of stars.
Yeah.
Day in, day out for 10,000 generations. It's just not sustainable for any civilization we can imagine right now.
And on top of that, you have to think about it from the other side, from the transmitting civilization's perspective. If they're 1,000 light years away, why should they waste enormous power focusing their beam directly on our solar system? They've got 50,000 other potential star systems in their neighborhood.
Right. They might just see our sun as just one of many thousands.
Exactly. The distant ETI might rationally decide to just exclude the solar system from their target list. If we don't present an obviously superior target for life, why dedicate gigawatts of power over those distances when the energy cost is so high and the return on investment is so uncertain? Distance doesn't just mute their signal, it makes their motivation to even transmit to us in the first place just vanish.
So the distance problem is twofold. It exponentially increases the number of targets we have to watch, making the search astronomically expensive and long. And at the same time, it decreases the chance that the other civilization even decided to target us in the first place. That's a deeply depressing set of constraints for radio astronomy.
It forces us to confront the reality that radio waves are just incredibly inefficient for dialogue across galactic distances. Even if a signal were sent, finding it in the cosmic background noise across 50,000 directions over centuries of monitoring. It's a scenario that's just designed for failure.
Okay, so we've established distance as the brute force killer. But Shklovsky and Bracewell realize there's an even sneakier assassin in the cosmos, and that is time itself. It's not enough that the galaxy has billions of stars and planets. The critical question is whether intelligent, technological life exists at the same time as us. Are they actually contemporary?
Right. I mean, if we only considered the physical longevity of a planet and its star, the picture would be bright. If life, once it achieves technology, just persisted for billions of years, as long as its stars on the main sequence, then the galaxy would be absolutely saturated. We'd be tripping over civilizations. KSI would be true. Distances would be small.
But our own history, and arguably the Fermi paradox itself, suggests that technological civilizations might have a pretty short shelf life.
And this is the crucial insight. Both researchers zeroed in on it almost at the same time, back in 1960. It all hinges on the duration of the technological era. We call it delta. And delta is just the length of time a civilization is technologically advanced enough to do interstellar communication, whether that's with radio or rockets.
And if that delta is small, say, limited by resource depletion or social collapse or, self-destruction, the whole galactic equation just changes.
It changes radically. A short delta means the number of currently existing civilizations, which we'll call n sub c, it decreases dramatically. And if n sub c drops, the average distance between these fleeting little islers of technology, it increases exponentially. You're basically trying to find a flash in the pan, a technological existence that might last only 10,000 years within a galactic timeline of billions of years. The probability of overlap just plummets.
So the brevity of technological life makes the universe seem profoundly emptier than it might actually be, purely because we're separated by time, not just space.
Exactly. Even if a civilization is physically capable of contacting its neighbors, if it only lasts for a brief period. The thousands of years required for interstellar communication to bear any fruit means that civilization will probably vanish before any useful dialogue can even begin. That forces the ultimate constraint on the search. We have to find someone who is contemporary and relatively close.
Okay, so how do we visualize this? You mentioned Bracewell's graphs.
Yes. To illustrate this crushing inverse relationship between technological longevity delta and interstellar distance to Bracewell developed a series of graphs. Shklovsky includes one as figure 47. Since we're in an audio medium, let's just describe what this visual relationship represents.
Okay, so we're picturing a graph. On the vertical axis, we have 3 key factors: longevity, delta, the number of coexisting civilizations, n sub c, and the number of stars to check, n sub d. And these are all plotted against the average distance d to the nearest civilization on the horizontal axis.
And what just jumps out at you immediately is this sharp inverse curve. As the line representing delta dives down, showing a civilization only lasts for a shorter period, the line for D, for distance, it just shoots vertically upward. This graphically illustrates the loneliness problem. A brief lifespan equals vast, isolating distances.
And the graph doesn't just show the distance, it also tracks n sub d,
Yeah.
the sheer number of stars we have to check within that distance. That's the logistical killer.
Yes. So let's walk through this specific, deeply sobering example from the source material. And this assumes a reasonable number of life-bearing planets have evolved high technology in our galaxy.
Let's use the assumption that the technological era, delta, is only 10,000 years, which, to us, that sounds like a long time, 4 times the length of recorded human history.
Cosmetically, 10,000 years is a blink. But if delta is 10,000 years, the distance to the nearest civilization, deed, according to Bracewell's calculation, it jumps to about 1,000 light years.
1,000 light years. So now we've moved firmly into the realm of case 2, where we have to monitor this massive sphere of space. How many stars does that 1,000 light-year radius actually contain?
Well, that volume contains n sub d, the number of suitable stars, which the analysis places at approximately 50,000. That is the number of targets we would have to monitor continuously for centuries, hoping to catch a signal from a civilization that might have launched it 1,000 years ago
Yeah.
and might now be technologically extinct.
50,000 stars. And a 2,000-year dialogue delay. This is why traditional electromagnetic communication becomes prohibitively difficult if technological longevity is limited. The effort is astronomical, and the chances of success are just vanishingly small because of that massive uncertainty factor.
The uncertainty is paramount. The issue isn't whether they can transmit, it's whether we can afford to check 50,000 directions over the millennia required. The moment delta drops below millions of years, distance becomes so large that radio dialogue just fails. We simply don't have the time to find them, and they don't have the time to await a response.
This realization that the combined effect of that radius cube distance and a short delta makes passive listening an inefficient exercise in futility, this is the pivot point. It forces us to ask, if radio fails, what is the technological workaround?
And that leads us right to Bracewell.
So we've established that distance and the brevity of technological eras are the twin killers of the radio search. We need a fundamental shift in strategy, one that doesn't rely on two-way light-speed exchange. This is where we transition to Bracewell's truly imaginative and, more importantly, logistically sound alternative, the physical automatic probe.
The underlying logic is simple but profound. If advanced civilizations exist, they will inevitably experience what he calls exceptional progress in rocket technology. Moving beyond their home planet is an unavoidable evolutionary step. And if you have the rocketry, you don't need to shout across 1,000 light years and wait for an echo. You can send a persistent, patient messenger.
So the advanced civilization, the sender, takes on the heavy lifting of the interstellar journey. It effectively eliminates that massive dialogue delay for the recipient.
Precisely. Bracewell proposed that civilizations wouldn't send these grand, multi-generational crewed ships. Those are resource-intensive, they require enormous life support systems. Instead, they would dispatch relatively small, highly automated rocket probes toward nearby stars. These are dedicated, resilient, self-sustaining emissaries. They're artifacts, not communication channels in the traditional sense.
Let's talk about the physics needed to make this work. We're talking about covering 1,000 light years eventually. But first, maybe a local network up to 100 light years. What kind of speeds do these probes have to achieve?
The analysis suggests the necessary technology would allow probes to reach speeds in the range of, say, 100,000 to 200,000 kilometers per second. This is roughly 300 to 600 times faster than the chemical rockets we use today.
That sounds like science fiction, but this analysis was done based on projected advances in the 1960s. To get those speeds, we're talking about things like controlled nuclear pulse propulsion, or maybe early concepts of fusion drives, aren't we?
Oh, absolutely. It moves way beyond chemical constraints into the realm of nuclear or even antimatter propulsion concepts, even if they were highly theoretical at the time of writing. And crucially, even at 200,000 kilometers per second, these speeds are still non-relativistic, and this is a key engineering advantage. They avoid the extreme time dilation and the exponential energy costs associated with getting close to the speed of light. It keeps the engineering problem manageable.
But if the nearest civilization is 100 light years away, a probe traveling at this speed still takes several centuries to get there. That's a long deployment time.
It is, but the source material estimates that it would take only several centuries for a high-tech civilization to establish a network of these robotic probes around all stars up to 100 light years away that are suspected of supporting life. You have to think of it as a civilization-wide infrastructure project.
Right.
But the payoff is guaranteed, persistent contact, which overcomes the potential shortness of their own technological lifespan. They deploy the network now, and it lasts indefinitely, achieving a long-term stability that the parent civilization might lack.
And the guidance system. It must be almost impossibly sophisticated. It'd have to navigate interstellar space for centuries and then perform these autonomous terminal maneuvers.
That's the most demanding technical requirement. The probes have to be capable of highly automated control, navigating immense distances, and then achieving a precise landing into a nearly circular, stable orbit around the target star system. This demands AI-level autonomy for course correction, for avoiding obstacles, and for optimizing its final orbital insertion. It's a feat of resilient, long-term autonomous navigation that ensures the probe becomes a stable, long-term artificial satellite, the cybernetic guest.
For a device to sit out there in the void for centuries or maybe millennia, just acting as a patient listener,
Yeah.
what sort of design resilience are we talking about?
Longevity is everything. The probe design has to incorporate robust protection against degradation. We're talking about shielding against cosmic radiation and, critically, protection against high-velocity meteoric bombardment. Even tiny particles traveling at high speeds can incapacitate delicate electronics over long durations. It needs, triple redundancy and self-repairing capabilities.
And then there's the power supply. How do you keep powerful radio equipment running for thousands of years? You can't just throw a battery pack on it.
The power source is the most ingenious part of the solution. The probe requires either a powerful nuclear source carried on board, a miniaturized, long-lasting fission or fusion reactor, or, more likely, the capacity to harvest energy from the star they orbit once they get there. By settling into a stable orbit around the target star, they gain access to a continuous energy supply. They turn the star system itself into their battery.
And that power shift leads directly to the core advantage of the probe method. The initial signal from the sender still travels across interstellar space, but the actual communication to the recipient planet, that's local.
That is the ultimate logistical cheat. Once it's in orbit, the probe is powered by the local star, and the signal it sends only has to cover the distance between the probe and the target planet, millions of kilometers. This distance is millions of times shorter than the interstellar gap. It completely circumvents the need for the sending civilization to transmit astronomical amounts of energy across hundreds or thousands of light years.
It's the difference between powering a continent-sized beacon and shining a flashlight across a small lake. It moves the challenge from physics, how much power can we generate, to engineering, how long can we keep this flashlight working?
And this advantage eliminates the burden on the recipient. We no longer need that continuous gargantuan sky service monitoring 50,000 stars. The probe does the monitoring for the sender and acts as a continuous, high-power local beacon directed specifically at the one habitable planet in the system.
And finally, the Bracewell method solves the wavelength problem. The classic SETI approach was always reliant on finding a mutually agreed-upon frequency, like the 21-centimeter hydrogen line.
That reliance on a specific wavelength, the cosmic water cooler, was a vulnerability. If a probe is sitting in local orbit, powered by the sun, and broadcasting a powerful local signal, the precise frequency it uses becomes much less important. The sheer local strength of the signal means it will be picked up regardless of minor frequency disagreements. This freedom from wavelength dependence further solidifies the probe method as superior for establishing first contact.
Okay, so the probe arrives. It's been traveling for centuries. What does it do?
Once this cybernetic guest successfully settles into its orbit, a mission that may have taken centuries, it initiates its standard pre-programmed operating procedure. It's all optimized for drawing maximum attention with minimum interaction risk.
What's the very first action it takes? Is it just broadcasting a loud hello?
Not initially, no. The first step is passive listening and comprehensive scanning. The probe automatically searches a wide range of frequencies for any evidence of technological activity coming from the planet. Specifically, it's looking for monochromatic radio signals, which are almost always artificial. It's waiting for the natives to reveal themselves.
So it's acting as a silent, invisible sentinel, waiting for the equivalent of a broadcast TV signal leak. And if it hears us,
If signals are detected, the probe's immediate duty is to act as a simple, powerful relay station. It immediately sends those detected signals back toward the planet, unchanged but boosted by its immense local power source.
Why the relay? Why not just transmit complex data right away?
The relay is a brilliant psychological and technological trigger. This repeated procedure detecting local signals and broadcasting them back as a strong, non-natural echo is designed to force awareness. The indigenous intelligent beings, us, we realize we are receiving an echo or a relayed signal from an object that is clearly artificial, located just outside the orbit of our outer planets. This achieves that crucial first step, awareness of the distant civilization's messenger, the cybernetic guest, without the messenger having to reveal its ultimate purpose immediately. It confirms the artifact's presence.
Okay, so once that awareness is established, the nature of the communication can shift. The probe can move from a simple relay to transmitting complex, pre-programmed information. This is where the millennia of preparation by the sender civilization finally pays off.
And the source material highlights the potential use of broadcast television technology here. The probe, using the newly detected signals from the recipient civilization as a cue, could transmit a TV image of the constellation, but with one critical element highlighted, the exact location of the star system it came from.
That is an elegant solution to the identification problem. It provides an immediate visual return address, telling us exactly where to look next.
Yes. The sending civilization, having gone through the exhaustive process of calculating the spatial coordinates needed to accurately depict their home star relative to the recipient's sky, they use this visual data transfer. They are telling the aborigines of the other world, using that older term, we sent this and this is where we are.
Once we, the recipient civilization, receive that information and realize the start of origin, the entire dynamic changes. We move from passively listening to actively pointing all our resources at one specific, verified target.
And the analysis projects the result. Once the receiving civilization knows the precise location, they will dispatch powerful modulated optical and radio beams, or even their own automatic probes, toward that specified star. The outcome, according to the source material, is a lively bilateral connection established within several centuries of the initial artifact discovery. The probe effectively collapses the vast interstellar distance into a local, actionable discovery.
And I imagine if the civilization is advanced enough, the information stored within the probe could be massive. It could contain encyclopedias, scientific primers, maybe a full history of the sending civilization. A one-sided data dump even before the recipient has mastered interstellar travel.
The source material even suggests that for a truly large-scale, galaxy-spanning communication infrastructure, these probes could be supplemented by intermediate interstellar relay stations, rockets systematically sent out into space to relay signals detected by the local probes back to the mother planet. It speaks to a civilization that views galactic communication not as an episodic search, but as a permanent technological utility, like a cosmic internet backbone.
This all leads us to the most unsettling and intriguing question raised by Bracewell. If this is the inevitable communication strategy for highly advanced civilizations, could such probes already be operating in our solar system, patiently waiting for us to achieve the necessary technical level to notice them?
The implication is that we have to shift our vigilance. We shouldn't just be looking for signals coming from 1,000 light years away. We have to carefully study all cosmic radio signals originating within our own solar neighborhood, looking for evidence of artifacts. Bracewell specifically drew attention to long-standing phenomena that lacked easy rational explanation, hypothesizing they might be evidence of these cybernetic guests.
And the centerpiece of this speculation is the famous long-delayed radio echoes, the LDEs.
The LDEs are truly fascinating. They were initially discovered in the late 1920s by researchers like Stormer and Vanderpool. They found that sometimes a radio signal would be transmitted from Earth, and a few seconds or even a few minutes later, an exact echo of that signal would return.
A normal radio echo comes back nearly instantaneously, right? Bounced off the ionosphere or maybe the moon. A delay of several seconds or minutes implies an incredible distance traveled.
Exactly. The mathematics of the time delay is unforgiving. A delay of several minutes requires the signal to have been reflected off a specific object located over 1 million kilometers away from Earth. That's far beyond the orbit of the moon and well outside the normal electromagnetic influence of our planet. Natural objects that are dense, specific, and reflective at those distances are extremely difficult to explain through conventional physics.
So the question arises, could these strange, long-delayed reflections be caused by a controlled artificial reflector, a cybernetic guest, that arrived centuries ago and is simply maintaining a stable orbit far out in our system?
It remains one of the most compelling non-conventional explanations for LDEs. The probe wouldn't necessarily be broadcasting continuously, but if it were designed to reflect or relay local signals to demonstrate its presence, it perfectly fits the LDE description.
But the source material is quick to caution us about our own capacity for missing even powerful local signals, which suggests the LDE data should be treated carefully.
That cautionary tale is essential to maintain scientific rigor. Look at the example of Jupiter's radio emission. Jupiter emits radio waves at tens of megahertz, reaching a power of 1,000 watts per hertz, a powerful local cosmic signal. Yet, because the signals were erratic, high frequency, and initially unexpected, they were repeatedly detected by researchers, but often dismissed, overlooked, or misinterpreted as atmospheric disturbances or local interference for decades. It wasn't until 1954 that the source was finally definitively identified as Jupiter.
Wow. So if we can miss or misinterpret a high-power radio source within our own solar system for 20 years, imagine how easy it would be to overlook the much more subtle, intermittent signals or reflections from a highly automated, self-sustaining probe designed for millennia of stealthy operation.
It just underscores the necessity of hypervigilance and open-mindedness when analyzing anomalous signals. The possibility of the cybernetic guest residing in our backyard is the direct logical consequence of applying Bracewell's strategy to galactic communication.
So on a grand scale, what does this all mean?
Well, if we accept the Bracewell hypothesis, that the systematic exploration of the universe by advanced civilizations relies on physical probes, this implies a high degree of organization. If these civilizations coordinate their efforts to ensure non-duplication of research, this leads to a powerful, galaxy-wide structure.
This sounds like galactic infrastructure, not just isolated communication.
Precisely. The source posits that this systematic, non-duplicative approach could lead to the existence of a great ring of reasonable civilizations spanning the galaxy. It echoes the organized, harmonious galactic community described in I.A. Efremov's classic science fiction novel Andromeda Nebula. It's a network based on mutual awareness, persistent communication links, and planned exploration zones.
That's a beautiful image. But the analysis also forces us to confront the harsh reality of years of searching for these probe signals. If we fail to find any evidence of a cybernetic guest in our solar system,
That leads to the little comforting conclusion. If thorough, careful searches over a prolonged period do not detect any source of artificial radio signals within our solar system, no local beacon, no anomalous echo, then the only logical deduction is that the nearest technologically developed civilization is simply too far away to have successfully established contact with us.
meaning they're outside that 100,000 light-year radius that allows for practical probe deployment within a reasonable time frame, or they just haven't started the project yet.
Yeah.
It suggests a profound galactic loneliness.
Let's just revisit the numbers from Figure 47 one last time, just to understand how quickly that window of opportunity closes when the technological lifespan is short. We looked at 10,000 years. But what if the technological era is even shorter?
What happens if the duration of the technological era, delta, is only 1,000 years? That's barely long enough for us to move from the Industrial Revolution to where we are now.
In that extreme scenario, the numbers become catastrophically unfavorable for any contact, even by probe. The average distance d to the nearest civilization increases dramatically to 2,000 light years. And the number of stars we'd need to check within that volume, n sub d, it skyrockets to 10 million.
10 million targets. That search space is impossible. And for the civilization attempting the initial contact, the travel time of their probes completely negates their ability to ever receive a reply.
Absolutely. A civilization existing for only 1,000 years simply does not have the necessary lifespan to establish contact with neighbors 2,000 light years away, even using high-speed probes. The travel time alone would consume twice their entire technological existence. It makes meaningful bilateral connection a statistical and temporal impossibility. This is the stark implication of the short-lived technology hypothesis.
It seems like any civilization that hopes to achieve galactic communication must first conquer internal stability. They have to achieve a minimum duration of technical operation far, far exceeding what we have seen on Earth so far.
And that necessity for longevity leads directly to the concept of the exception, the supercivilization. Even in the bleakest scenario, where most civilizations vanish after a brief 1,000-year technological spasm, a tiny fraction might manage to overcome the internal and external forces that cause rapid demise. They avoid self-destruction, they solve resource issues, and they achieve an exceptionally high level of technical development maintained over an astronomical duration.
How long would their technological era, their delta, need to be to overcome these constraints?
We're talking about civilizations existing for millions or tens of millions of years. If a civilization's lifespan was 10 million years, they would have had ample time to investigate not just the local neighborhood, but thousands of neighboring stars. Deploying vast networks of Bracewell probes, they would possess immense cosmological knowledge.
But then we run into the final, slightly humbling sociological implication. Even if these super civilizations exist, the source suggests they might not find us worthy of detailed investigation.
That's the sobering perspective. These immensely ancient and stable civilizations might view developing civilizations like ours, which have only existed technologically for a few hundred years, as embryonic or transient. Our level of development would be so vastly different from theirs that we wouldn't register as a high priority target for contact or resource expenditure.
It's the moth analogy.
Yes, exactly. Shklovsky uses this vivid image that millions of short-lived, unstable civilizations might be like moths being born and dying somewhere in our galaxy twice a year on average. Why would a civilization that has mastered galactic scale spend resources tracking every fleeting phenomenon? The silence of the universe in this case might not be due to a lack of life, but rather a lack of interest, because we haven't proven our stability or maturity yet.
So the Bracewell hypothesis offers two potential explanations for the lack of contact. Either we are separated by time and vast distance, or the only civilizations close enough to care are so advanced that they find us too primitive to bother with. Both conclusions really challenge our anthropocentric view of the cosmos.
They really do.
So this deep dive into the synthesis of Shklovsky and Bracewell has given us a completely new framework for the search for ETI. We've confirmed that once distances exceed, say, 100 light-years, the combined problems of spherical volume and short technological lifespans make traditional radio communication an exercise in futility. It demands impossible resources over impossible timescales.
The key takeaway is the power of the artifact. Physical, automated probes overcome both the vastness of space and the potential brevity of technological eras. The method cleverly shifts the burden from the recipient maintaining a costly, continuous sky service to the probe acting as a self-contained, autonomous, high-power local beacon. This means the search for ETI must fundamentally become a search for artifacts, a search for logistics, not just messages.
We have to remain vigilant, not just for radio messages coming from distant stars that might have died 1,000 years ago, but for reflections, gravitational anomalies, or strange energy signatures here in our own solar system. We might be looking up at the sky when a forgotten cybernetic guest has been patiently orbiting the sun for centuries, waiting for us to finally pay attention.
And that leaves us with a final thought for you, the learner. Given that Bracewell's concept suggests advanced civilizations view the deployment of resilient, long-lasting probes as inevitable, what physical, long-lasting evidence might we leave behind for future, far-flung civilizations to find? If we accept the idea that our technological era might be short-lived, or that our radio signals are inefficient across galactic distances, what form should our message take, knowing it needs to survive for millions of years, patiently waiting for a recipient? That challenge of designing for deep time is the ultimate engineering problem posed by the necessity of the interstellar probe.